Good morning and welcome to this video course on advanced hydrology. My name is Ashu Jain. I am Associate Professor in the Department of Civil Engineering at IIT Kanpur. If you would need to contact me for any reason, for clarifying any doubts or asking any questions, you can contact me through email at this address. If you can remember my name, Ashu Jain, that is ASHUJAIN at iitk.ac.in, and you can also call me at this number. This course has been designed to present the principles of advanced hydrology at a PG level or a postgraduate level. The basic knowledge of hydrology would be desirable in this course, however, it would not be necessary. At the end of the course, a serious student is expected to have a thorough understanding of various components of the hydrologic cycle and the statistical tools that are useful in hydrology. I have underlined the components of hydrologic cycle and the statistical tools, which basically means that there are two components of this course, in which one we would look at the components of hydrologic cycle from the conceptual point of view, and other is from the statistical point of view. Coming to the contents of the course, I would like to just give you a very brief background about the course initially. These are the contents. First, we will look at the hydrologic cycle, the water balance, systems concept and hydrologic model classification. Then we would look at what is called a Reynolds transport theorem. It is a basic equation which models the movement of fluid, any kind of fluid, and in our case it will be water, and all the three basic equations, that is continuity equation, momentum equation and energy equation, can be derived from this Reynolds transport theorem. Then we would look at the hydrological processes, that is atmospheric water, precipitation, evaporation, surface flow, subsurface flow and groundwater flow. We would go into the hydrograph analysis, that is unit hydrograph and various response functions and their interrelationships. Then we would be moving to hydrologic statistics, in which we would look at the statistical parameters, how we fit a probability distribution to a given set of data, testing the goodness of fit, frequency analysis and carrying out the reliability analysis. Now, coming to the course plan, that is basically some detailed topics and approximate number of lectures in each topic. Among the introduction, we would look at the hydrologic cycle, the water budget equation, the world water quantities, residence time, systems concept, transfer function operators, hydrologic model classification. All of this I expect to take about 3 lectures. Then moving to the hydrological processes, we would look at the derivation of the Reynolds transport theorem, then derivation of continuity, momentum and energy equation from the Reynolds transport theorem, and we look at the discrete time continuity. This is expected to take about 3 lectures. Each lecture would be about 1 hour. Then in the third module, we move to the atmospheric water or atmospheric hydrology, in which we would look at the atmospheric circulation, water vapor, formation of rainfall, types and forms of precipitation, precipitable water, monsoon characteristics in India, the rainfall measurement, density and adequacy of rain gauges. Then we would look at what is called a thunderstorm cell model, out of which we will get the rainfall intensity, we will derive an expression. IDF relationships, that is intensity, duration, frequency relationships, spatial averaging of rainfall, factors affecting evaporation, estimation and measurement of evaporation, energy balance method, aerodynamic method and Priestley-Taylor method and pan evaporation. All these things will take about 8 lectures. Continuing, the fourth module will consist of subsurface hydrology, in which we would look at the soil moisture profile, the porosity, saturated and unsaturated flow, Richards equation, infiltration, Horton's equation, Phillips equation and Green-Empt methods, and then parameter estimation and ponding time concepts. All of this will take about 4 lectures. In the surface water, we would look at the catchment storage concept, the Hortonian and saturation overland flow concepts, stream flow hydrographs, base flow separation, phi index, ERH and DRH concepts, algorithm for abstraction using Green-Empt equation, SCS method, overland flow and channel flow modeling, time area concepts and the stream flow networks. All of this would take about 6 lectures. Then we come to the hydrograph analysis, in which we would look at the concept of unit hydrograph, the general hydrologic system model concept, the response functions of a linear hydrologic system, and their interrelationships, the convolution equation, the definition and limitations of the UH and instantaneous unit hydrograph, the derivation of the unit hydrograph for a single and a complex storm, and optimization of a UH using the data and different techniques such as regression and linear programming methods. You would also look at the synthetic unit hydrograph towards the end. So, all of this will take about 6 lectures. Then we move to the hydrologic statistics, in which we would look at the probability concepts, random variables, the laws of probability, PDFs and CDFs, normal and binomial distributions, statistical parameters, the expected value, variance, skewness and peakedness, fitting a probability distribution, methods of moments and maximum likelihood, testing the goodness of fit using the chi-square method, and probability plotting method, extreme value distributions, frequency factors, log Pearson distribution, etc. And this is expected to take about 8 lectures. Towards the end of this course, we will move to the groundwater hydrology, and we would spend about 7 hours in that, in which we would look at the occurrence of groundwater, aquifers and their properties, Darcy's law, permeability, transmissibility, stratification, confined groundwater flow, unconfined groundwater flow under Dupit's assumptions, well hydraulics, steady flow into the confined and unconfined wells, and unsteady flow in the confined aquifers. For this course, I will be following these books mainly: Applied Hydrology by Venti Chow, David Maidment and Larry Mays, which is published by the McGraw-Hill Publications. And the second book or the reference I would like to follow in this course is Engineering Hydrology by K. Subramanya. It is published by Tata McGraw-Hill Publishing Company in New Delhi. So, with this brief overview of the course, we would like to get started. Okay, so first of all, we would look at, as the name suggests, the name of this course is Advanced Hydrology. So, the first question I would like to answer is, what is hydrology, or how do we define hydrology? As a layman, or for any person, what is hydrology? First, we will look at the definition of hydrology. For a layman, what is hydrology is? It's simply science of water. However, if we get little technical, what is hydrology is? It is defined as the occurrence, distribution and circulation of water. As we know, the water is constantly moving in different parts of this earth, in the atmosphere, on the land and in the ground. When we talk of the occurrence, distribution and circulation of water, it may be either in the gaseous phase or in the water vapor form or in the liquid phase. And when we talk of its circulation, it is in the hydrosphere, in the atmosphere, that is about 15 kilometers above the earth. All right. So, as a practical hydrologists, we are interested in the movement of water about 15 kilometers from the ground into the atmosphere. Into the ground, we are focused more on the lithosphere, which is about 1 kilometer below the ground. Okay. Whenever we talk about hydrology, any book you follow, you will deal with what is called a hydrologic cycle. As we know that the water is constantly moving in different parts of the hydrologic cycle or different phases on the earth. It is a closed loop system in which the water starts evaporating from the ocean. So, what we will do is we will look at this hydrologic cycle, let us say starting from ocean. Okay. And then we may also have condensation. Due to the heat energy that is provided by the sun, the water starts evaporating from oceans in the form of clouds, and due to the wind action, it moves over the land masses. Okay. And then onto the land, it will precipitate in the form of precipitation. And this precipitation can be in any form. There are various forms of precipitation which we will look at little later in this course. So, it could be either rain, it could be hail, snow, and many other different forms. Okay. Part of this precipitation again can become evaporation, or from land it will become evapotranspiration, and part of it will become what is called runoff. Okay. What happens to this runoff? This runoff finally goes into the ocean through streams and rivers. Okay. And part of this precipitation which falls on the earth becomes infiltration. Infiltration is the part of water or precipitation that goes into the ground, as we know, and this then percolates deep and goes into the groundwater. This groundwater also, after a very long time in the form of base flow, goes back to oceans through the rivers and streams on the land. From the groundwater, we do some manual interaction, and then we take the water out for water supply, and from runoff also we take water manually for different various purposes. So, we see that the water is moving in different parts of the earth in various phases, in liquid as well as gaseous phase, and all of this interaction is extremely complex, and thorough understanding of the basic governing principles of movement of this water are necessary to model the hydrologic cycle. Now, before we move on, we would like to look at the basic concept, or one main fact about this hydrologic cycle is what is called the water budget, which says that the total amount of water or water resources are constant. When we say the total water resources are constant, we mean that we are applying what is called the water balance equation, or famously it is known as the continuity equation. The continuity equation, which can be applied to any phase of the hydrologic cycle, basically states that input minus output is the change in storage. Now, this equation, as we see, it should be dimensionally homogeneous. So, we define our I is the inflow volume in a catchment during time delta t. So, we are writing this equation at some particular time duration delta t, which could be a day, which could be a week, a month, or even an year. Similarly, O is the output or outflow volume from a catchment during the same time delta t, and the delta S is the change in storage of the catchment during the same time delta t. Okay. Now, this equation can be applied to any small component of a hydrologic cycle. For example, we can apply this to the whole catchment, or we can apply this to a small reservoir or dam, or we can apply this to underground water or any different parts of the hydrologic cycle. So, for catchment, we write different inputs and outputs which are physically existing in the catchment. So, the main input is the precipitation. There could be runoff out of it, the groundwater flow component, the evaporation, there may be some transpiration, and all of that should sum equal to the change in storage in the particular catchment. We can apply this to the lake, in which we will have precipitation in a lake, plus there may be some upstream inflow, all right, water coming as the surface runoff into the lake, minus there may be some surface outflow from the lake, there will be some evaporation, there may be some seepage losses, and all of that should be equal to the change in. Okay. And this is a very useful equation, continuity equation or the water balance equation, through which we can manage our water resources for a lake or for a dam or for any catchment. Now, moving on, the next thing I would like to look at is the importance of hydrology in the form of what is called water quantities. The total quantity of water that is available on earth is approximately 1386 million kilometer cube. This includes all the water that is available on the earth. We know most of it is contained in oceans, which is approximately 96.5%. And as you know that the sea water is saline and it is not useful for human consumption or for any useful purpose for that matter. So, the remaining water which is on the land, out of that 1% is saline. So, we have about 3.5% of water on land which is saline and not useful again. That leaves us about 2.5% of the total water which is fresh water on land which will be useful, and this comes out to be approximately 35 million kilometer cubed of water which is fresh on the land. However, out of this 35 million kilometer cubed of water, approximately 10.6 million kilometer cube is liquid, and the remaining about 24.4 million kilometer cubed of water is solid. Okay. And the solid water is in the form of frozen ice, and it is contained on the or exists on the mountain tops in the form of glaciers and frozen ice in the polar region. So, this is all the water we have that is available for us for any kind of water management on the earth. This water has remained constant over the years, okay? And certain United Nations approximations or estimations suggest that this will be sufficient up to 2050. Why? Because of the industrial growth and economic expansion and so on, the consumption of water is increasing every day. Population is also increasing. So, we do have sufficient water today, but the demand will exceed the water supply by about 2050. So, we need to utilize our water resources, we need to understand the various forms of water, how it is occurring, so that we take care of it very carefully and we use it optimally using engineering methods. Moving on, the next I would like to look at a very important concept of what is called a residence time. As we have seen in the hydrologic cycle that the water occurs in the atmosphere, in the rivers, underground, in the oceans and various places on the earth. However, it will spend different amount of time in each phase of the earth, and residence time will help us in understanding and modeling that particular phase. First of all, looking at the definition, it is the average time taken by a particle of water to pass through a phase of the hydrologic cycle is known as or is called the residence time. Of that particular phase. How can we calculate it? This is nothing but the volume of water in that phase divided by the net rate of flow in that particular phase. Okay. So, what we will do next is I would like to look at an example of how we calculate the residence time. And we will look at the example of the global rivers. Okay, if we look at the residence time of global rivers, we can find the volume of water in global rivers approximately as 0.00212 million kilometer cube. Okay. And these numbers I am taking are from United Nations approximations, and we will look at them a little later. The average flow rate which has been estimated of water in the global rivers is approximately 44,700 kilometer cubed per year. So, as we see that the time duration here is annual or 1 year. So, we are approximating the total amount of water that runs off or the runoff or total volume in all the rivers of the world taken together. If we sum that all up, it will be approximately 0.00212 million kilometer cube. So, using these two numbers, we can find out the residence time for global rivers as 0.00212 times 10 to the power 6, that is kilometer cube, divided by 44,700 kilometer cubed per year, and that will come out to be about 0.04743 years and approximately 7.31 days. Okay. So, this way we can find out, or we know that on an average approximately when the water enters any of the rivers, it spends about 17 days in that river, and this number is, as I said, global average. In different parts of the world this number may vary. Okay. So, rivers which are very steep, it may be less time, and very flat or long rivers it may be slightly more, but on an average that is what it is. How this number is useful? We can compare the residence time, for example, for atmospheric water. If we find it out using the United Nations approximations of total volume of water in the atmosphere and the average flow rate, that is precipitation or condensation, it comes out approximately about 3 days. Okay. So, in the atmosphere the water spends about 3 days, and in the rivers it spends about 17 days. So, it tells us about the accuracy of the hydrological modeling. For example, the atmospheric water system is highly dynamic. All right, the atmospheric conditions or the climatic conditions can change dramatically within a matter of hours, in fact. All right, so that kind of system will be difficult to model as compared to the other system, which is or in which the residence time is more or water spends more time. Similarly, if we find out the residence time, these are just approximate numbers I am writing. For groundwater, it is approximately of the order of 2 to 3 years. Okay. What does that mean is, once the water enters into the ground, it takes about 2 to 3 years to come out of it. All right. So, it spends a lot of time. All right. So, it is easy to track its movement and carry out the modeling process. Now, as I was talking about, how we get this number is using the world water quantities or this data from the United Nations approximations. This table shows the global annual water balance in different parts of the earth. For example, runoff to ocean, you see rivers kilometer cube per year, which we just took in this example, is 44,700. In groundwater, it is 2,200. That is the approximate rate of groundwater flow towards the ocean. Total runoff is that much, and in millimeters per year is that much. So, you see that these are the world water quantities which United Nations has approximated, which are very handy in making certain calculations. The other table, which is estimated world water quantities, it talks about the total volume of ocean water is 1338 million kilometer cube, and it is the percentage of total. Similarly, the groundwater, we see the fresh water is about 10.53 million kilometer cube, which forms about 0.76%, and so on. Okay. So, moving on, now we will look at an example of lake water balance. We looked at the water budget equation for the catchment. So, we will look at the lake water balance. How the continuity equation can be extremely useful in finding out different components or estimating some of the things which will help us in managing the water resources. The initial water level in the lake is given to us. Let us say it is S1 is 103.2 meters, and all these numbers are above an assumed datum. Okay. The average inflow, these are the data which are given to us into the lake. Is about 6.0 meter cube per second, and it is from surface sources. The average outflow from the lake that is given to us is 6.5 meter cube per second. So, this is your, let us say, I, and this is your Q. The surface area of the lake is given to us about 5,000 hectares. The average rate of rainfall in the month on the lake P is about 145 millimeters, and the rate of evaporation is about 6.10 centimeters, and the time period we are looking at is a month. All these numbers are during a month. So, these are the data or what is given to us, and what we have to find is A, write the water budget equation for the lake, and B, calculate the water surface elevation at the end of the month. So, to solve this problem, we just need to write the continuity equation, that is inflow minus outflow is equal to change in storage, and inflow components are given to us, and there are two inflow components in this case. One is the surface inflow and other is the precipitation, and as far as the outflows are concerned, there is surface outflow Q and also the evaporation. So, if we write the water budget equation, this is the general continuity equation, or we can write I bar delta T plus P times A. This is I, where I bar is the average rate of inflow into the lake, and we multiply this by the delta T because the equation has to be dimensionally homogeneous. So, it is in volumetric units, and then precipitation is in the length unit. So, we need to multiply this by the area of the, or the surface area of the lake, minus Q delta T plus evaporation. These are the outflows from the lake, and all of that has to be equal to the change in storage. So, this is your equation or answer to the part A of this question. Now, delta T we know is 1 month. We can convert it into seconds. So, it will be assuming 30 days, 24 hours, 60 minutes, 60 seconds, it will be approximately 2.592 times 10 to the power 6 seconds. So, I delta T will be equal to 6.0 meter cube per second times 2.592 times 10 to the power 6 seconds. Seconds cancel out. So, it will be approximately 15.552 million meter cube. Okay. So, this is the total volume of water that enters into the lake in the whole month. Now, similarly calculating the average outflow from the lake, this would be 6.5, which is meter cube per second again, and we multiply this by the time, and it will be approximately 16.848 million meter cube. The other components are P times A, which would be 14.5 centimeters over 100 in the meters. So, this is the amount of precipitation that falls on the lake during the month in meters, and this we multiply by the surface area, which is 5000 hectares, which is a plot of 100 meters by 100 meters, and if I divide by 10 to the power 6, my answer would be in million meter cube. So, that we have all the quantities in the same units. Similarly, we find out the evaporation losses from the lake. It will be 6.10 centimeters divided by 100. So, this will be in meters multiplied by same thing, and this also will be in million meter cube. Okay. So, now what we can do is, we have calculated all the 4 quantities. We can put this in the water budget equation. Therefore, we will have delta S is equal to 15.552, that was the inflow, plus 7.25 is the precipitation, minus 16.848 is the outflow, surface outflow, and minus 3.05 is your evaporation losses, and all these numbers are multiplied by 10 to the power 6, so that this is in meter cube. You simplify that, it will be 2.904 10 to the power 6 meter cube, and which will be equal to 2.904 times 10 to the power 6. We want to convert this into the length units, so we multiply this by the area or the surface area of the lake, which is 5000 hectares, multiplied by 100 meters and 100 meters. So it will be about 0.058 meters. So this is the change in storage, or actually I should write this as delta Z, and this delta Z then is nothing but Z2 minus Z1. From here you can find that the lake elevation at the end of the month will be equal to delta Z plus Z1. Alright, so it will be equal to 0.058 plus the initial level was 100.200 meters. That would mean your Z2 is 103.258 meters. Okay, so this way we see that we can find out the lake elevation at the end of the that particular month. So we see that we use the continuity equation to solve a problem of the lake water balance. So with that we come to the conclusion of today's lecture, and tomorrow we will start with the systems concept.